every diagram you have ever seen of the solar system is lying to you. Those neat classroom posters showing 8 colourful planets lined up next to each other like beads on a string have left a picture in your head that is physically, emotionally, and mathematically wrong. The real distance between the planets is so extreme that if you built an accurate scale model with the Sun the size of a basketball, Neptune would sit half a mile away, and Earth itself would be nothing more than a grain of sand lost in an ocean of empty pavement. The solar system is not a compact family of neighbouring worlds. It is a chain of isolated outposts separated by gulfs so savage that even light takes hours to cross them. If you want to see how empty and brutal our own solar system truly is, go ahead and hit that like button and subscribe. It helps more than you think, and we genuinely appreciate every single one of you. Now settle in and get yourself comfortable. Let's begin. Close your eyes and picture the solar system. Whatever appears in your mind right now is wrong. Not slightly off, not a rough approximation that gets the general idea right. The image in your head is so catastrophically distorted that it has more in common with a fairy tale than with the physical reality of the space you actually live in, and you are not alone. Almost every human being on this planet carries the same broken mental picture, and almost every one of them got it from the same source, a classroom poster. You remember the one, the Sun on the left side, big and glowing, then Mercury, Venus, Earth, Mars, Jupiter, Saturn with its gorgeous rings, Uranus and Neptune. Lined up like ornaments on a shelf, the planets were colourful, the spacing looked reasonable. Maybe the outer planets were a bit farther apart than the inner ones, but the whole thing fit neatly onto a single piece of paper pinned above the whiteboard. You looked at it 1,000 times, and every time your brain absorbed the same silent message. The planets are neighbours. They sit near each other, they share a common space. The solar system is a compact, tidy family of worlds. That message is one of the most deeply embedded scientific lies in modern education. Not because anyone intended to deceive you, but because the truth cannot physically fit on a poster. Here is the problem. The solar system contains 2 categories of information that are both extremely important, but that exist at completely incompatible scales. The first category is the size of the planets. Jupiter is roughly 11 times wider than Earth. Saturn is about 9.5 times wider. Mercury is roughly a third of Earth's diameter. These ratios are big, but they are manageable. You can draw circles on a page that represent these size differences pretty accurately and still have room for labels. The second category is the distance between those planets. And this is where everything collapses. The distance between Earth and Mars at their closest approach is roughly 55 million kilometers. The distance between Earth and Jupiter is roughly 600 million kilometers at its nearest. The distance from the Sun to Neptune is approximately 4.5 billion kilometers. These gaps are so absurdly enormous compared to the size of the planets themselves that no drawing, no poster, no diagram, and no documentary animation can show both categories on the same image at the same scale and still be readable by a human eye. If you wanted to draw the Sun as a circle the size of a basketball, roughly 24 centimeters across, then the Earth at the correct scale would be a grain of sand sitting about 26 meters away. Mars would be an even smaller grain, roughly 40 meters from the basketball, and Neptune would be a peppercorn sitting roughly half a mile down the road. Your poster would stretch for half a mile. The planets would be invisible specks. The space between them would be absolutely empty. Nobody would hang that on a classroom wall. So instead, every diagram in every textbook does the only thing it can do. It cheats. It compresses distance. It pulls the planets in toward each other until they all fit on a single page. It preserves the rough order of the planets from the Sun outward. It might even get the relative sizes roughly correct, but it obliterates the distances between them by factors of thousands. And in doing so, it quietly rewires your intuition to believe that the solar system is a place where planets sit relatively near one another, close enough to feel like parts of a connected whole. They do not. And the first place this illusion starts cracking is the most familiar piece of the solar system, the inner planets. You would think the inner solar system would be the cozy part. Mercury, Venus, Earth, Mars. 4 rocky worlds huddled near the sun, the terrestrial planets, the warm neighborhood. Compared to the frozen reaches of the outer planets, this should feel compact and intimate. It does not. But before we measure the distances between these worlds, we need to confront a subtler distortion that has been quietly shaping your expectations for decades. We need to talk about the Moon. The Moon is the only world beyond Earth that human beings have ever visited. Between 1969 and 1972, 12 astronauts walked on its surface. The journey from Earth to the Moon took roughly 3 days. 3 days. That is a long weekend, a short vacation, a time frame that fits comfortably inside human experience. You can feel 3 days. You can plan around 3 days. When you hear that astronauts traveled to another world and came back within a week, your brain registers space travel as something that operates on human timescales. Difficult, yes. Dangerous, certainly. But fundamentally reachable. The Apollo missions left a subconscious yardstick embedded in the public imagination. Space is far, but we crossed it. The next step must be the next world out. That yardstick is a trap. The Moon sits roughly 384,000 kilometers from Earth. Light crosses that distance in about 1.3 seconds. Communication between Houston and the Apollo astronauts was essentially real-time. When something went wrong on Apollo 13, Mission Control and the crew collaborated second by second, improvising solutions in a continuous back-and-forth conversation that saved 3 lives. The Moon was close enough for help, close enough for conversation, close enough for rescue. Mars, the next plausible destination for human explorers, is not close enough for any of those things. At its very nearest, Mars is roughly 140 times farther from Earth than the Moon is. At its most distant, it is more than 1,000 times farther. The Apollo astronauts reached the Moon in 3 days. A crew heading for Mars would need 7 to 9 months. The Moon was a sprint across a river. Mars is a voyage across an ocean, and the ocean has no islands, no ports, and no way to turn back once you have committed to the crossing. The Moon gave humanity a taste of space travel that was, in cosmic terms, misleading. It was the closest thing the solar system had to offer, and it set an expectation of reachability that no other destination in the solar system will honor. To understand why, you need to meet the unit that astronomers use to measure distances inside the solar system. It is called the astronomical unit. 1 astronomical unit equals the average distance between the Earth and the Sun. That is approximately 150 million kilometers, 93 million miles. Already, that number resists comprehension. 150 million kilometers is a distance so large that if you drove a car at highway speed non-stop, it would take roughly 170 years to cover it. A commercial jet would need about 17 years. Even light, the fastest thing in the universe, takes 8 minutes and 20 seconds to cross that gap. Every beam of sunlight warming your face right now left the sun over 8 minutes ago. If the sun vanished this instant, you would continue to see it shining for another 8 minutes before darkness arrived. That is 1 astronomical unit, 1. And the inner solar system already stretches beyond it. The Moon, by comparison, is roughly 0.0026 astronomical units from Earth. A rounding error. A speck of distance so small it barely registers on the scale that the planets actually use. Everything that human beings have ever accomplished in space, every orbit, every spacewalk, every lunar landing, has occurred within a fraction of 1% of 1 astronomical unit. The interplanetary distances that follow make everything humanity has achieved so far look like wading into the shallows and declaring that you have crossed the sea. Mercury orbits the Sun at an average distance of roughly 0.4 astronomical units, about 58 million kilometers. Venus sits at roughly 0.7 astronomical units, about 108 million kilometers from the Sun. Earth is at 1 astronomical unit. Mars orbits at roughly 1.5 astronomical units, approximately 228 million kilometers from the Sun. These numbers sound orderly when listed on a page. They even look reasonable when plotted as dots on a simple number line, but they conceal a brutal physical reality. The gap between each of these worlds is not a short hop, it is an abyss. Consider Venus, our closest planetary neighbour. Venus approaches Earth more closely than any other planet, sometimes passing within about 38 million kilometres. That is closer than Mars ever gets. Yet even at that minimum distance, light takes over 2 minutes to travel from Earth to Venus. A spacecraft travelling at the speed of a bullet, roughly 1,700 kilometers per hour, would need roughly 2.5 years to cross that gap, and that is the closest any planet ever comes to us. The average distance between Earth and Venus is much larger, roughly 170 million kilometers, because the two planets spend most of their orbits on opposite sides of the Sun from each other. This is the first critical concept that diagrams destroy. Planetary distances are not fixed. They are constantly changing. Every planet in the solar system orbits the Sun at a different speed along its own elliptical path. Mercury races around in just 88 Earth days. Venus takes 225 days. Earth takes 365 days. Mars takes 687 days. Because they all move at different rates, the relative positions of any two planets shift continuously. Sometimes Earth and Mars are on the same side of the Sun, relatively close together. Other times they are on opposite sides, separated by the entire diameter of their combined orbits. This means the distance between Earth and Mars is never a single number. It is a range, and that range is savage. At their closest possible approach, Earth and Mars can be separated by roughly 55 million kilometers. This happens during what astronomers call opposition, when Mars and the Sun are on opposite sides of Earth's sky. But this minimum distance does not occur at every opposition. Because Mars follows an elliptical orbit, some oppositions bring the planets closer than others. The closest approach in recent decades occurred in 2003, when Mars passed within roughly 56 million kilometers of Earth. That was the nearest the two planets had been in almost 60,000 years. But at their most distant, when both planets sit on opposite sides of the Sun, the separation between Earth and Mars can exceed 400 million kilometers. That is more than 7 times the minimum distance. The planet we talk about colonizing, the world that fills headlines about future human settlement, drifts between 55 million and 400 million kilometers from us, depending on nothing more than where both planets happen to be in their orbits at any given moment. This is not a minor fluctuation. This is a 7-fold change in distance driven by orbital geometry alone, and it has enormous consequences. When NASA plans a mission to Mars, the entire launch schedule revolves around this orbital dance. Favourable launch windows, the periods when a fuel-efficient transfer between Earth and Mars is possible, open only once every 26 months. Miss that window and you wait more than 2 years for the next one. The missions themselves do not fly in a straight line. They follow curved trajectories called Hohmann transfer orbits, long elliptical paths that arc outward from Earth's orbit to intersect with Mars's orbit months later. A typical Hohmann transfer to Mars takes roughly 7 to 9 months. Not because the spacecraft is slow, but because the distance is immense and the physics of orbital mechanics demands patience. During that transit, the crew or the robotic probe is completely alone, suspended in a void between two worlds with nothing around it for millions of kilometers in every direction. No space station to dock at, no fuel depot to visit, no emergency shelter to reach, just empty space, radiation, and silence. And here is where the first real shock lands. Even after the spacecraft arrives at Mars, even after it lands and begins its mission, the distance between that crew and Earth continues to change every single day. The communication delay between Earth and Mars is not a fixed number. It fluctuates from roughly 3 minutes at closest approach to approximately 22 minutes at maximum separation. That means a simple question sent from mission control to a Mars crew could take 22 minutes to arrive. The crew's answer would take another 22 minutes to travel back. A single exchange, one question and one response, could take 44 minutes. Nearly 3/4 of an hour of waiting for a reply to a sentence that took 5 seconds to speak. This is not a technical problem waiting for a better antenna. This is physics. Radio signals travel at the speed of light. Light is the fastest thing in the universe. No technology will ever make this delay shorter. It is woven into the structure of space itself. A crew on Mars cannot have a conversation with Earth. They can exchange messages. They can send reports and receive instructions. But the kind of real-time back-and-forth communication that humans rely on for collaboration, for emotional support, for emergency response, simply does not exist at interplanetary distances. If something goes catastrophically wrong on Mars, a distress signal would take up to 22 minutes to reach Earth. Even if mission control reacted instantly, their instructions would take another 22 minutes to arrive back at Mars. That is 44 minutes of helplessness baked into the geometry of 2 orbits. And Mars is the closest realistic destination for human exploration beyond the Moon. And then, periodically, even that delayed link goes silent. Roughly every 26 months, Earth and Mars drift into a configuration called solar conjunction. The Sun passes directly between the 2 planets. From Earth's perspective, Mars disappears behind the Sun. From Mars's perspective, Earth does the same. During this alignment, radio signals travelling between the 2 worlds must pass through or near the Sun's corona, the superheated outer atmosphere of plasma that surrounds our star. The corona is turbulent, electrically charged, and dense enough to scatter, distort, and absorb radio transmissions. The interference is so severe that reliable communication becomes impossible. NASA does not attempt to fight through it. Instead, the agency enforces a full communication blackout. For roughly 2 weeks, sometimes longer, no commands are sent to rovers on the Martian surface. No data is received from orbiters above it. Every spacecraft operating at Mars is placed into a pre-programmed safe mode before conjunction begins, loaded with enough autonomy to survive without hearing from Earth until the geometry clears. For robotic missions, this blackout is a nuisance. Curiosity and Perseverance pause their drives. Orbiters store data until the link reopens. No one panics. But for a human crew on Mars, solar conjunction would mean something far more severe. 14 days of absolute silence, not delayed messages, not degraded signal quality, nothing. No voice calls, no text uplinks, no weather warnings from Earth about incoming solar particle events, no medical consultations, no morale calls to family. For 2 weeks, the crew would be more isolated from the human species than any group of people in history, sealed inside a habitat on a frozen desert world with no communication link to anyone outside it. And this is not a contingency plan for a worst-case scenario. It is a scheduled, predictable, physically unavoidable event that occurs every single synodic period. Any long-duration Mars surface mission will face it at least once. A 3-year mission will face it twice. It is written into the orbital mechanics of 2 planets circling 1 star, and no technology can prevent it, because no technology can move the Sun out of the way. This is what the changing distance between planets actually means in practice. It is not just that communication gets slower when the planets drift apart. It is that the orbital geometry periodically severs the link entirely. Distance in the solar system is not merely an obstacle. It is a rotating, shifting, sometimes absolute barrier that opens and closes on a schedule dictated by gravity and governed by no human authority. Now pull back and look at the inner solar system as a whole. 4 small rocky worlds separated by tens of millions to hundreds of millions of kilometers of vacuum. The distances between them change constantly. Travel between any 2 of them requires months of flight through empty space. Communication suffers delays ranging from minutes to nearly half an hour, and periodically it vanishes completely. And this is the dense part. This is the region where the planets cluster most tightly around the Sun. This is the neighborhood that textbook diagrams present as a cozy ring of nearby worlds. There is a reason the inner solar system feels deceptively compact. Your brain did not evolve to handle these numbers. Human spatial reasoning was shaped by the African savanna. Our ancestors needed to estimate the distance to a predator, the time to reach a water source, the range of a thrown spear. The largest distances the human brain needed to process for survival were a few kilometers at most. We developed superb intuition for scales up to maybe 100 kilometers. Beyond that, distances become increasingly abstract. 1,000 kilometers means a long drive. 10,000 kilometers means an international flight. But 100 million kilometers has no experiential anchor. Your brain cannot visualize it, feel it, or instinctively grasp it. So it does what brains always do when confronted with incomprehensible information. It substitutes something simpler. It rounds down. It compresses. It turns 100 million kilometers into feels far but reachable and moves on. Classroom diagrams exploit this cognitive shortcut without meaning to. They present the planets at distances your brain can process, a few centimeters apart, and your spatial reasoning accepts that as approximately real. From that moment on, the solar system lives in your head as a place where planets are roughly as far apart as cities on a map. And that mental model is not just inaccurate, it is dangerously misleading. Because it sets up expectations about travel time, about communication, about rescue, about the difficulty of reaching other worlds, that the actual solar system will demolish without mercy. Consider what the inner solar system looks like if you strip away every visual cheat and present it honestly. Imagine you are standing in the middle of a vast empty desert. The sun is a bonfire behind you. Mercury is a tiny marble, sitting roughly 60 meters away across flat open sand. You can barely see it. Venus is another small marble, 110 meters away in a different direction, because the planets do not line up. It is a dim speck at that distance. Earth, your home, is a marble 150 meters away, and Mars is a marble roughly 230 meters off. Between each of these marbles there is nothing. No landmarks, no features, no signs of structure, just flat, featureless emptiness in every direction. And the marbles themselves are so small that you would lose sight of them almost immediately. You would walk for minutes between each one, seeing nothing, hearing nothing, finding nothing. The inner solar system at honest scale is not a neighborhood. It is a wasteland with occasional specks. And remember, this desert model only shows average distances. The actual distances shift constantly as the planets orbit. Mars drifts closer and farther from Earth by hundreds of millions of kilometers over the course of every synodic period. Venus swings between its nearest point and its farthest point on timescales of months. Even Mercury, the smallest and fastest inner planet, varies its distance from Earth significantly as it whips around the Sun every 88 days. The solar system is not a still photograph, it is a slow-motion dance of orbiting worlds, and the gaps between those worlds stretch and compress ceaselessly. The number you see in a textbook for the distance between two planets is an average, a mathematical convenience. The actual distance at any given moment might be half that average, or twice it, depending entirely on where the two planets happen to sit in their orbits right now. This perpetual motion adds a layer of cruelty to interplanetary travel that static diagrams completely erase. When mission planners calculate a trajectory to Mars, they are not aiming at where Mars is. They are aiming at where Mars will be 7 months from now, when the spacecraft finally arrives. They must account for the orbital velocities of both Earth and Mars, the gravitational influence of the Sun, and the precise geometry of a transfer orbit that will intersect with a moving target, hundreds of millions of kilometers away, after months of silent coasting through empty space. If any of those calculations are wrong, if the launch window is missed by even a few days, the entire mission must be postponed for 26 months until the orbital geometry aligns again. 2 years of waiting because two small rocky worlds were out of position relative to each other. That is the tyranny of planetary distance. It does not just make trips long, it dictates when trips can happen at all. The inner solar system also offers a subtle warning about what lies ahead. Notice the spacing. Mercury is roughly 0.4 astronomical units from the Sun. Venus is at 0.7, Earth at 1, Mars at 1.5. The gaps between these worlds are roughly a third of an astronomical unit, then a third again, then half a unit. They increase, but gently. The jumps are measured in tens of millions of kilometers. Substantial, yes. Mind-bending for human intuition, absolutely, but still within the same order of magnitude. Beyond Mars, the pattern breaks. The next planet outward is Jupiter, and Jupiter does not sit at 2 astronomical units, or 2.5, or even 3. Jupiter orbits at 5.2 astronomical units from the Sun. The gap between Mars and Jupiter is roughly 3.7 astronomical units, over 550 million kilometers of empty space. That single gap between Mars and Jupiter is larger than the entire distance from the Sun to Mars. The jump is not incremental. It is explosive. The solar system does not expand gently as you move outward. It detonates. The distances between successive planets grow larger and larger in a pattern that accelerates toward numbers the brain simply refuses to hold. And if the inner solar system, the compact part, the cozy part, the part where every diagram in every textbook makes the planets look like friendly neighbours, is already this empty, this spread out, this brutally hostile to human travel and communication, then the outer solar system is going to be something else entirely. Everything you thought you understood about how far apart the planets are is about to get much, much worse. Beyond Mars, the solar system stops pretending. The inner planets gave you fair warning. They showed you that even the closest worlds are separated by tens of millions of kilometers of nothing. They showed you that communication delays are already measured in minutes. They showed you that orbital motion turns distance into a moving target that never holds still. But the inner solar system was still, in a sense, gentle. It was the prologue, the introduction, the throat clearing before the scream. Because out beyond Mars, between that small red world and the next recognizable planet, sits a gap so enormous it would swallow everything you have encountered so far and still have room to spare. And on the other side of that gap, waiting in the cold, the distances between planets stop being merely large and start becoming something that the human mind was never built to process. The first thing you cross is the asteroid belt. And the first thing you need to know about the asteroid belt is that every movie you have ever watched lied about it. Science fiction trained you to imagine a dense field of tumbling boulders, rocks clanking against each other, spacecraft weaving and dodging through a lethal obstacle course. The reality is the opposite. The asteroid belt stretches from roughly 2.2 to 3.3 astronomical units from the Sun. That is a band of space, about 150 million kilometers wide. Within that enormous volume, the total mass of every asteroid combined, every single rock in the entire belt, adds up to roughly 4% of the mass of our Moon. If you gathered every asteroid together and packed them into one object, you would get something smaller than Earth's moon by a staggering margin. The belt is not a wall. It is not a barrier. It is a scattering of lonely pebbles separated by millions of kilometers of vacuum. When NASA sends spacecraft through the asteroid belt, they do not need to dodge anything. The odds of accidentally hitting an asteroid are estimated at less than 1 in a billion. The belt is emptiness, decorated with the occasional grain of rock. And yet even this sparse, thinly scattered rubble field sits in a gap that dwarfs the entire inner solar system. Mars orbits at 1.5 astronomical units. Jupiter orbits at 5.2. Between them lies 3.7 astronomical units of open space, roughly 550 million kilometers. To grasp what that means, consider this. The total distance from the Sun all the way out to Mars is about 228 million kilometers. The gap between Mars and Jupiter alone is more than twice that. You could fit the entire inner solar system, from the Sun to Mars, inside the Mars to Jupiter gap, and still have hundreds of millions of kilometers left over. The diagram in your head shows Mars and Jupiter as the next two beads on a string, separated by a modest hop. The physical reality is that Jupiter sits on the far side of a void so wide that everything you have learned about planetary distance up to this point fits inside it with room to breathe. When you finally arrive at Jupiter, you have entered a different solar system. The scale has changed. The rules of distance that govern the inner planets no longer apply. Jupiter orbits at an average of approximately 778 million kilometers from the Sun. Light from the Sun takes about 43 minutes to reach it. That means if you were standing on one of Jupiter's moons and you looked at the Sun, the light hitting your eyes would be 43 minutes old. The Sun you were seeing would be the Sun as it looked nearly 3/4 of an hour ago. Events happening on the Sun right now would remain invisible to you for the better part of an hour. That disconnect between the present moment and the arrival of information becomes the defining feature of life in the outer solar system. You are not just far from the Sun, you are separated from it in time. Jupiter's distance from Earth is even more punishing because it shifts just as relentlessly as the Mars-Earth distance does, except on a grander scale. When Earth and Jupiter sit on the same side of the Sun, the distance between them shrinks to roughly 588 million kilometers. When they are on opposite sides, it balloons to approximately 968 million kilometers. That range, from roughly 600 million to nearly a billion kilometers, fluctuates over a cycle of about 13 months as Earth laps Jupiter in their respective orbits. A signal sent from Earth to Jupiter takes between 32 and 52 minutes depending on where both planets are at that moment. A round-trip exchange, one message out and one reply back, takes over an hour at minimum and nearly 2 hours at worst. Think about what that means for a spacecraft operating near Jupiter. Every command sent from mission control is already old by the time it arrives. Every response from the spacecraft is already old by the time it reaches Earth. If a probe encounters a problem, if a thruster misfires or a sensor fails or a trajectory needs correcting, the ground team will not know for at least half an hour. Their corrective command will not arrive for another half hour. By the time the loop closes, an hour has passed. In the unforgiving environment of deep space, an hour is an eternity. This is why every mission to the outer solar system must be designed with a level of autonomy that inner solar system missions can sometimes avoid. Jupiter spacecraft cannot be flown like remote control cars. They must think for themselves, react to threats on their own, and execute pre-programmed contingency plans without waiting for human approval. The distance imposes independence whether the engineers want it or not. Now move outward to Saturn. If Jupiter felt remote, Saturn introduces a new register of isolation. Saturn orbits the Sun at an average distance of approximately 1.4 billion kilometers, 9.5 astronomical units. The gap between Jupiter and Saturn alone is about 4.3 astronomical units, roughly 650 million kilometers. That single jump from one planet to the next covers nearly as much distance as the entire span from the Sun to Jupiter's orbit. The outer solar system does not expand in polite increments. Every gap is bigger than the one before it, often dramatically, each new planet separated from the last by a void wider than everything you have already crossed. Light from the Sun takes roughly 79 minutes to reach Saturn, roughly an hour and 20 minutes. When the Cassini spacecraft orbited Saturn from 2004 through 2017, every image it sent back to Earth took between roughly 67 and 85 minutes to arrive depending on orbital positions. Scientists on Earth would transmit a command to repoint the camera. The command would travel at the speed of light across 1 billion kilometers of empty space. Then the data would travel back along the same path. The total cycle from instruction to result routinely exceeded 2.5 hours, and Cassini was one of the most successful planetary missions in history. It operated beautifully for 13 years. But every single moment of that mission was conducted across a delay so large that most people on Earth would lose patience waiting for a web page to load in a fraction of the time. The Cassini mission also illustrates something else, about outer solar system distances. The spacecraft did not fly straight to Saturn. It could not. A direct trajectory from Earth to Saturn using chemical propulsion would require an impractical amount of fuel. Instead, Cassini was launched in October of 1997 and followed a winding path through the inner solar system, using gravity assists from Venus twice, then Earth, then Jupiter to build up the velocity needed to reach Saturn's orbit. The spacecraft arrived at Saturn in July of 2004, nearly 7 years of flight. Not because the spacecraft was slow, Cassini reached speeds exceeding 70,000 kilometers per hour during its gravity assists, but because the distance was so immense and the energy requirements so extreme that the only practical route involved looping through the inner solar system multiple times before heading outward. 7 years of coasting through empty space to reach a planet that sits on the same page as Earth in every textbook diagram you have ever seen. Beyond Saturn, the solar system enters a realm that most people have never seriously thought about. Uranus orbits the Sun at an average distance of approximately 2.9 billion kilometers, 19.2 astronomical units. The gap from Saturn to Uranus is roughly 9.7 astronomical units, approximately 1.4 billion kilometers. That single gap is larger than Saturn's entire distance from the Sun. Pause and let that register. The empty space between Saturn and Uranus, the space that contains no major planets, no significant landmarks, nothing but vacuum and stray particles and darkness, is wider than the entire distance from the Sun to Saturn. You could drop the Sun, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter and Saturn into that gap and they would not fill it. Only one spacecraft has ever visited Uranus. Voyager 2 flew past it in January of 1986, over 8 years after its launch. At the time of that flyby, radio signals from Voyager 2 took approximately 2 hours and 45 minutes to reach Earth. Commands sent back took the same amount of time to arrive at the spacecraft. The communication round trip was nearly 5.5 hours. Voyager 2 had a single chance to observe Uranus as it flew past at high speed. There was no time to wait for instructions from Earth. Every observation sequence, every camera angle, every instrument measurement had been programmed months in advance and loaded into the spacecraft's computer. The flyby was essentially conducted on autopilot because the distance made real-time human involvement impossible. And the data that Voyager 2 collected during those few hours in January of 1986 still constitutes the vast majority of what we know about Uranus today. We have not been back. No mission is currently en route. That single brief encounter, conducted by a spacecraft that had already been flying for nearly a decade, remains our only close look at an entire planet. Then comes Neptune, the outermost recognized planet, the edge of the planetary solar system. Neptune orbits at an average distance of approximately 4.5 billion kilometers from the Sun, 30 astronomical units. Sunlight takes 4 hours to reach Neptune. When you look at Neptune through a telescope tonight, you are seeing it as it appeared 4 hours ago. Everything happening on Neptune at this exact moment will remain invisible to every telescope on Earth for the next 4 hours. The planet exists in a perpetual state of temporal separation from us. It is always in the past. Voyager 2 remains the only spacecraft to have visited Neptune. It flew past in August of 1989, 12 years after launch. 12 years. That single number should recalibrate your intuition about what the distance between planets actually means for human capability. Voyager 2 was one of the fastest objects ever built by human hands. It was travelling at roughly 19 kilometers per second, about 68,000 kilometers per hour, during its approach to Neptune. At that speed, you could circle the entire Earth in roughly 35 minutes. And even at that blistering velocity, Neptune was so far away that the spacecraft needed 12 years of continuous travel to reach it. During the Neptune flyby, The communication delay between Voyager 2 and Earth was approximately 4 hours and 6 minutes one way. A round-trip signal took over 8 hours. If mission controllers had spotted something unexpected in the data and wanted to adjust the observation plan, their command would not arrive at Voyager 2 for 4 hours. The spacecraft's response would not reach Earth for another 4 hours. By then, the flyby would be long over. Neptune would already be shrinking behind the spacecraft. Every critical decision had to be made in advance and embedded in the onboard computer. The humans who built and launched the probe were, in the most literal physical sense, unable to participate in the encounter as it happened. They could only watch the data arrive, hours late, and hope that every calculation they had made years earlier was correct. But there is another way to feel the distance to these outer worlds that no number on a page can deliver. It involves something you would actually see, or rather, something you would stop seeing. The sun gets dimmer, not metaphorically, not slightly. It fades with the square of the distance, and by the time you reach the outer planets, it has dimmed so profoundly that the experience of daylight itself has been stolen. On Earth, the sun fills the sky with blinding light. You cannot look at it without risking injury. At Jupiter, 5 times farther out, the sun delivers roughly 1/27th the light it provides on Earth. You could still see clearly by Jovian sunlight, roughly comparable to a heavily overcast day on Earth, but the sun itself would look noticeably smaller in the sky. A brilliant point of light rather than the overwhelming disk, you know. At Saturn, the sunlight weakens further, roughly 1% of what Earth receives. Noon on Titan would look like deep twilight on Earth, dim enough that you might struggle to read a page by the light coming through the haze. At Uranus, the sun delivers approximately 1/400th of the light Earth receives. At Neptune, it is roughly 1/900th. NASA has noted that high noon on Neptune would look like dim twilight to human eyes. The sun would still be the brightest object in the sky, brighter than any star by far, but it would no longer look like the sun, you know. It would be a fierce, brilliant point, a piercing dot of light suspended in blackness, too small to show a disk to the naked eye. You would know, intellectually, that it was the same star that warms beaches and grows forests back on Earth. But your eyes would tell you something different. Your eyes would tell you that you are somewhere else entirely. Somewhere the sun has become a distant lantern barely strong enough to cast a shadow. This dimming is distance made visible. Every outward step through the solar system takes you farther from the warmth and light that define everything humans have ever known. And by the time you reach the ice giants, the sun has retreated so far that its dominance over the sky has quietly been revoked. You are in a place where the nearest star, your star, the one your planet orbits, looks like a particularly bright point in a wall of darkness. And here is the detail that truly transforms your understanding of the outer solar system. The distances between these worlds are not fixed any more than the inner planet distances are. Jupiter, Saturn, Uranus, and Neptune all orbit the Sun at different speeds on different elliptical paths. Jupiter takes roughly 12 Earth years to complete one orbit. Saturn takes roughly 29 years. Uranus takes 84 years. Neptune takes 165 years. Because they move at vastly different rates, the relative positions of any two outer planets change continuously over timescales that span decades. The distance between Jupiter and Saturn varies from roughly 650 million kilometers when they are on the same side of the Sun to approximately 2.2 billion kilometers when they are on opposite sides. That is a variation of over 1.6 billion kilometers, driven purely by orbital positioning. The distance between Saturn and Neptune varies even more wildly, from roughly 3 billion kilometers when they are at their nearest, to nearly 6 billion kilometers at their most distant. These are not stable separations. They are constantly shifting quantities that swell and contract over cycles measured in human lifetimes. A mission to Neptune does not face one distance. It faces a moving target whose separation from Earth changes by billions of kilometers depending on when you launch and how long the journey takes. The spacecraft we have sent to the outer solar system provide the sharpest possible contrast between the diagram in your head and the reality of interplanetary space. Consider New Horizons, the mission that flew past Pluto in July of 2015. New Horizons was launched in January of 2006 aboard an Atlas V rocket and left Earth at a velocity of roughly 58,000 kilometers per hour, the highest launch speed ever achieved by a human-made object at that time. Even at that tremendous speed, the spacecraft needed 9.5 years to reach Pluto. And Pluto, at the time of the flyby, was roughly 33 astronomical units from the Sun. Just 3 astronomical units beyond Neptune's orbit. 9.5 years of flight at record-breaking speed for a destination that sits barely beyond the outermost planet. New Horizons passed through Jupiter's orbital distance in just 13 months, picking up a gravity assist that boosted its speed even further. But from Jupiter outward, the distances grew so vast that even those enhanced velocities could not prevent years of silent coasting. Between Jupiter and Pluto, the spacecraft travelled for 8 additional years through a void so empty that its instruments recorded essentially nothing. No planets, no moons, no asteroids of any significance. Just the slow crawl of a dot crossing an immensity that would reduce any diagram to absurdity if drawn at honest scale. But the void between Jupiter and Pluto did not merely test the spacecraft. It tested the humans behind it. 8 years is not just a trajectory number. It is a span of time during which an entire mission team on Earth had to keep a project alive, funded, staffed, and technically sharp, while the spacecraft they had built drifted through emptiness with almost nothing to report. Engineers who had designed the probe's instruments had to maintain operational proficiency on hardware they could not meaningfully interact with for the better part of a decade. Scientists who had staked their careers on the Pluto flyby had to find ways to remain productive and professionally viable during years when no new data existed. Budget cycles came and went. Political administrations changed. Congressional priorities shifted. Graduate students who joined the project around the time of launch had defended their dissertations and moved on to other positions before the flyby data arrived. Some team members retired during the cruise phase. Others died. The mission outlasted portions of its own team because the distance between Jupiter and Pluto imposed a silence so long that human careers and human lives could not hold still long enough to match it. This is a cost of interplanetary distance that rarely appears in mission summaries. The void between planets does not just challenge propulsion systems and communication links. It corrodes the human institutions built to cross it, keeping a team together, keeping funding flowing, keeping expertise intact across a gap measured in years of nothing, is an organizational endurance test that mirrors the physical endurance test faced by the spacecraft itself. The solar system's distances are so extreme that even the people who never leave Earth are punished by them. Consider also the Voyager missions in aggregate. Voyager 1 and Voyager 2 were launched in 1977. They used a rare alignment of the outer planets that occurs roughly once every 175 years to visit multiple worlds in sequence. Voyager 2 visited Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. That is 4 planets across 12 years of continuous flight. Think about what was happening on Earth during those 12 years. Personal computers went from novelties to household items. The Berlin Wall stood at its height and then fell. Entire generations of children were born, started school, and entered their teenage years. And throughout all of that, Voyager 2 was still in transit, still crossing the gaps between planets, still climbing outward through a solar system that simply refused to end. But what those dates conceal is what happened between the flybys. After Voyager 2 swept past Saturn in August of 1981, it did not encounter Uranus until January of 1986. That is 4.5 years of travel between 2 planetary encounters. 4.5 years during which the spacecraft crossed roughly 10 astronomical units of open space, roughly 1.5 billion kilometers, and found nothing. Its cameras had nothing to photograph. Its spectrometers had nothing to analyze. The particle detectors measured the thin solar wind and the faint hiss of cosmic rays. The magnetometer tracked the slowly weakening magnetic influence of the Sun. That was it. For 4.5 years, one of the most sophisticated scientific instruments ever launched by the human species drifted through a void so empty that its primary scientific output was confirmation that the void was, in fact, empty. Then it flew past Uranus in a few frantic hours, collected a burst of data that would sustain an entire field of research for decades, and sailed onward into another 3.5 years of silence before reaching Neptune. The gaps between those 4 famous encounters were not just long, they were barren. They were the solar system showing, in real time, what actually occupies the space between the planets. Nothing. Measured, confirmed, recorded nothing. Today, nearly 5 decades after launch, Voyager 1 is approximately 165 astronomical units from the Sun. Voyager 2 is approximately 137 astronomical units out. Both spacecraft have left the heliosphere, the bubble of solar wind that surrounds the Sun, and entered interstellar space. And yet, even after 5 decades of continuous survival at roughly 17 kilometers per second, neither spacecraft has come anywhere close to leaving the solar system. The Oort cloud, the vast shell of icy objects that marks the outermost gravitational boundary of the Sun's influence, is estimated to begin at roughly 1,000 astronomical units and extend outward to perhaps 100,000 astronomical units. At their current speeds, the Voyager spacecraft will need roughly 300 years to reach the inner edge of the Oort cloud, and perhaps 30,000 years to pass beyond it entirely. 30,000 years. Modern human civilization is roughly 10,000 years old. Voyager would need 3 times the entire span of recorded history to exit the solar system completely, and the Voyager probes are already far beyond the orbit of the outermost planet. They have already crossed every gap between every planet. They passed Neptune's orbit in 1989. Everything since then has been traversal of the empty space beyond the planets, the vast uncharted wasteland that extends outward from the planetary zone, and that wasteland is orders of magnitude larger than the already immense spaces between the planets themselves. This is the reality that no diagram, no animation, and no classroom model can convey. The outer solar system is not a slightly stretched version of the inner solar system. It is a qualitatively different kind of emptiness. The gaps between planets grow explosively larger as you move outward. Each successive planet is separated from the previous one by a void wider than the total distance you have already covered. And the spacecraft we send to cross these voids do not zip between worlds the way diagrams imply. They crawl, they coast, they drift for years through an emptiness so absolute that the instruments on board can find nothing to measure. The spacing pattern itself reveals something deeply unsettling about the architecture of the solar system. The inner planets are separated by fractions of an astronomical unit. Mercury to Venus is roughly 0.3 astronomical units. Venus to Earth is roughly 0.3. Earth to Mars is roughly 0.5. These are relatively gentle steps. Then the gap to Jupiter explodes to 3.7 astronomical units. Jupiter to Saturn is 4.3. Saturn to Uranus is roughly 9.7. Uranus to Neptune is approximately 10.8. Each gap is not merely bigger than the last, it is often dramatically bigger. The distance between Uranus and Neptune alone is approximately 1.6 billion kilometers. A void so wide that it dwarfs the entire inner solar system many times over. The progression is roughly logarithmic. Each step outward multiplies the previous gap rather than merely adding to it. This is not a linear expansion like floors in a building growing slightly taller as you go up. It is a compounding expansion like debt accumulating interest. The distances grow faster than your ability to adjust. By the time you reach Neptune, the sheer scale of the separation between worlds has escalated so far beyond human reference that even the analogies start to fail. And here is the final blow before the story turns. Every one of these distances, every one of these gaps, every one of these years-long spacecraft transits represents the space between planets. objects that exist, destinations you can at least point to, name, photograph, dream about visiting. Between those destinations, there is nothing. Not darkness punctuated by interesting landmarks. Not a sparse field of objects you might explore along the way. Nothing. The space between Jupiter and Saturn is a void. The space between Saturn and Uranus is an even larger void. The space between Uranus and Neptune is an even larger void still. These are not corridors between rooms. They are oceans between continents. Except the oceans have no water, no currents, no islands, no life. They are pure geometric distance, empty in a way that no environment on Earth can approximate, stretching outward in dimensions that the human mind can track mathematically, but never truly feel. The outer solar system is not a place. It is an absence, a void with occasional interruptions. And if the distances between planets are already this extreme, if even our fastest machines need decades to cross them, then the question is no longer how far apart the planets are. The question is what those distances actually do to any attempt by human beings to reach them, communicate across them, or survive within them. That answer is the hardest part of this story. Distance is just a number until something goes wrong. You can hear that Jupiter is 5.2 astronomical units from the Sun and feel nothing. You can hear that Neptune sits 4.5 billion kilometers away and nod politely. Numbers on a page do not hurt. They do not frighten. They do not keep mission planners awake at 3 a.m, staring at trajectory charts and whispering the same question over and over. What if something breaks? Because out here, between the planets, distance stops being a measurement and becomes a weapon. It attacks communication. It destroys the possibility of rescue. It dictates when you are allowed to leave and when you must arrive. It transforms travel from an inconvenience into a sentence served in solitary confinement inside a metal tube hurtling through nothing. And the farther out you go, the sharper the blade becomes. Start with the thing humans take most for granted. Conversation. On Earth, communication is instantaneous. You speak. Someone hears, they reply. The delay between your words and their response is measured in fractions of a second. Even a phone call to the opposite side of the planet introduces a delay so brief that most people never notice it. This immediacy is not a luxury. It is the invisible foundation of every human system that depends on coordination, feedback, and trust. Emergency response works because a caller can describe a crisis and a dispatcher can react in real time. Surgery works because a team can communicate during the procedure. Air traffic control works because a pilot and a controller can exchange critical information within seconds. Remove that immediacy and every one of those systems collapses. Now extend a communication link to Mars. At its closest, Mars is roughly 55 million kilometers from Earth. A radio signal, traveling at the speed of light, takes just over 3 minutes to cross that distance. At first glance, 3 minutes sounds tolerable. Annoying perhaps, like a bad video call, but manageable. It is not. 3 minutes is only the one-way delay. The person on Mars speaks. 3 minutes later, Earth hears it. Earth responds. 3 minutes later, Mars hears the reply. That is a minimum 6-minute gap between one sentence and the answer to that sentence. And this minimum delay only occurs during the narrow windows when Mars is at its closest to Earth. For most of Mars's orbit, the delay is far longer. When Earth and Mars sit on opposite sides of the Sun, the one-way delay stretches to approximately 22 minutes. A round-trip exchange takes 44 minutes. A simple conversation consisting of 10 exchanges back and forth would take over 7 hours to complete. That is not communication, that is correspondence. It has more in common with exchanging letters in the 18th century than with anything a modern human would recognize as talking to someone. For robotic spacecraft, this delay is inconvenient but survivable. Mars rovers like Curiosity and Perseverance operate on daily command cycles. Each morning, Earth uplinks a set of instructions. The rover executes them throughout the Martian day. Each evening, the rover downlinks data describing what happened. Scientists review the data overnight and prepare the next day's instructions. The cycle repeats. It is slow and requires extraordinary planning, but it works because rovers are patient. They do not panic. They do not need emotional reassurance. They do not suffer from the psychological corrosion of isolation. Human beings are a different matter entirely. Imagine a crew of 6 astronauts living and working on the surface of Mars. They are the most highly trained individuals their space agency could produce. They have rehearsed every procedure, memorized every contingency, practiced every emergency response. And then something unexpected happens. A habitat seal fails. A dust storm damages a solar panel. A crew member suffers an acute medical emergency that falls outside the scope of their onboard medical training. On the International Space Station, any of these situations would trigger an immediate conversation with mission control. Engineers would assess the data in real time. Doctors would provide guidance moment by moment. Decisions would flow back and forth across a communication link fast enough to feel like collaboration. On Mars, none of this is possible. The crew reports the emergency. Then they wait. 3 minutes at best. 22 minutes at worst. Then mission control responds. Then they wait again. In the most favourable orbital geometry, the fastest possible back and forth exchange with Earth takes 6 minutes. In the worst geometry, it takes 44 minutes. During a medical emergency, during a structural failure, during any event where seconds matter, the crew on Mars is alone. Not alone in the poetic sense. Alone in the operational sense. No one on Earth can help them in real time. No one on Earth can see what they see, assess what they assess, or make decisions at the speed their situation demands. The crew must handle it themselves, with whatever knowledge, equipment, and composure they have on hand. Mission control becomes a distant advisor that sends messages the way a pen pal sends letters. Heartfelt, expert, and utterly useless in the moment of crisis. Now, push the delay outward. A crewed mission to the Jupiter system, if such a thing were ever attempted, would face one-way communication delays of 32 to 52 minutes. A round-trip exchange would take over an hour at minimum and nearly 2 hours at maximum. At Saturn, one-way delays climb to roughly 67 to 92 minutes. A crewed station orbiting Titan, Saturn's largest moon, could send a message to Earth and not receive a reply for nearly 3 hours. 3 hours. In 3 hours on Earth, an office worker attends 2 meetings, eats lunch, and responds to 30 emails. In 3 hours on a spacecraft near Saturn, a crew facing a life-threatening emergency receives exactly 1 response from home. The math is brutal, and the math is fixed. Light speed is not a technological limitation. It is a law of physics. No antenna, no relay satellite, no quantum communication scheme currently demonstrated can make information travel faster than light across interplanetary distances. The delay is permanent, it is structural, and it gets worse with every additional astronomical unit between the crew and Earth. This is where the concept of rescue dies. On Earth, the entire philosophy of human safety in hazardous environments is built on the assumption that help can arrive. Sailors carry distress beacons because Coast Guard helicopters can reach them. Mountain climbers carry satellite phones because rescue teams can be dispatched. Astronauts on the International Space Station have Soyuz capsules permanently docked as lifeboats, capable of returning a crew to Earth's surface within hours. The station orbits roughly 400 kilometers above the planet. Help is always close. The safety net is always there. In interplanetary space, there is no safety net. There is no rescue vehicle parked nearby. There is no second spacecraft on standby ready to launch at a moment's notice. And even if there were, the distances and travel times between planets make the concept of emergency rescue functionally meaningless. Consider the simplest possible scenario. A crewed spacecraft is 6 months into its transit from Earth to Mars. It is roughly halfway between the 2 planets, deep in interplanetary space. A catastrophic failure occurs. A meteorite strike punctures the hull. A fire destroys a critical system. The crew sends a distress signal. It reaches Earth in roughly 10 minutes. Mission Control immediately begins working the problem. But what can they do? There is no second ship ready to launch. Even if one existed, even if it were sitting on a launch pad fully fueled and crewed, the physics of orbital mechanics would not allow it to reach the stricken vessel for months. You cannot simply point a rocket at a moving target in space and fly there in a straight line. You must follow an orbital trajectory that accounts for the gravitational pull of the Sun, the velocity of both the rescue ship and the target, and the alignment of Earth and the target's position at the time of arrival. These trajectories take months. By the time a rescue ship could reach the stranded crew, the emergency would be long over, one way or another. This is not a failure of engineering. It is a consequence of geometry. The solar system is too large and the distances between objects in it are too vast for the concept of timely rescue to apply. A crew in transit between planets is on its own for the duration of the journey. Whatever happens to them, they must solve it with what they have aboard, or they do not solve it at all. Every interplanetary mission is, from the moment of departure, a self-contained island of human survival drifting through a void where no help exists. And the transit itself is its own particular form of torment. Consider what the months or years between planets actually contain for a human crew. On Earth, travel involves scenery. A road trip delivers changing landscapes. A sea voyage offers waves, weather, sunrises, and the occasional glimpse of marine life. Even air travel provides clouds, coastlines, and the slow rotation of continents beneath you. The human brain was built for environments that offer sensory stimulation. Our psychology depends on variation, novelty, the feeling that we are moving through a world that changes around us. Interplanetary transit offers none of this. The view from a spacecraft traveling between Earth and Mars is a fixed star field that does not perceptibly change from one week to the next. The stars do not grow larger. The destination planet, even months before arrival, is still indistinguishable from the stars around it, a pinprick of reflected light lost in a wall of identical pinpricks. The sun slowly shrinks behind you. The blackness outside the window is the same blackness it was yesterday, and the same blackness it will be tomorrow. There are no landmarks, no milestones, no visible sign that the spacecraft is moving at all, despite travelling at tens of thousands of kilometers per hour. The psychological literature on long-duration spaceflight calls this the monotony problem, and it is considered one of the most serious threats to crew mental health on any Mars-class mission. Humans deprived of sensory variation for months at a time develop symptoms that overlap with clinical depression, reduced motivation, impaired cognitive function, difficulty concentrating, increased interpersonal irritability. The mind, starved of input, begins to feed on itself, and the longer the transit, the deeper the monotony bites. A 7-month trip to Mars is challenging. A 2-year trip to Jupiter would be a psychological endurance test with no precedent in human experience. A decade-long transit to Neptune exists beyond the boundary of anything our species has ever attempted to plan for. The tyranny of distance also controls when missions can leave. You might imagine that a spacecraft can depart for Mars or Jupiter whenever it wants, the way an airplane can take off for any destination on any day. It cannot. The planets orbit the Sun at different speeds, and the relative geometry between Earth and any given destination changes continuously. A fuel-efficient transfer from Earth to Mars is only possible when the two planets are in a specific alignment. This alignment recurs roughly every 26 months. Miss that window and the next opportunity is over 2 years away. For Jupiter, favourable launch windows open roughly every 13 months. For Saturn, roughly every 12.5 months. For Uranus and Neptune, the windows open at similar intervals, but the transit times are so enormous that the distinction barely matters. Any mission to the ice giants requires a decade or more of flight regardless of when it launches. These windows exist because of the way orbital mechanics works. The most fuel-efficient path between two planets is an elliptical orbit that departs from one planet's orbital position and arrives at the other planet's orbital position at exactly the right time. This requires the two planets to be in a precise angular relationship at the moment of launch. If the geometry is wrong, the spacecraft would need vastly more fuel to compensate. Fuel that adds weight, complexity, and cost to a degree that quickly becomes prohibitive. So mission planners wait. They wait for years, sometimes decades, for the right alignment. The Voyager missions exploited a once-in-a-generation planetary alignment that will not recur until the 22nd century. That alignment allowed a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune in sequence, using each planet's gravity to sling the probe onward toward the next. Without that alignment, visiting all 4 outer planets with a single spacecraft would have been essentially impossible with chemical propulsion. The restriction on launch windows creates a cascading effect on mission design. A Mars mission is not just a 7 to 9 month journey, it is a 7 to 9 month outbound journey, followed by a stay on Mars that must last until the next favourable return window opens, followed by another 7 to 9 month return journey. A round trip to Mars from launch to landing back on Earth takes roughly 2.5 to 3 years. The crew cannot decide to come home early, because the orbital geometry will not allow a fuel-efficient return trajectory until the planets realign. They are committed, locked into a schedule dictated by the motion of 2 worlds around a star on a timetable that no amount of human urgency can accelerate. For the outer planets, the constraints are even more suffocating. A crewed mission to Jupiter, if one were conceivable, would require a transit time of roughly 2 to 6 years depending on the propulsion technology used. A stay in the Jupiter system would need to last until a return window opened. The total mission duration could easily span a decade. A mission to Saturn would be even longer, and any crewed expedition to Uranus or Neptune sits so far beyond current technological reach that even speculating about timelines feels reckless. The distances are too large, the transit times are too long, the communication delays are too severe, the isolation is too complete. This is where the emotional weight of planetary distance begins to settle. It is one thing to say that Neptune is 30 astronomical units from the Sun. It is another thing entirely to sit inside the implications of that number and feel what it does to human capability. At 30 astronomical units, you are beyond rescue. You are beyond a real-time communication. You are beyond any launch window that could bring you home in less than a decade. You are, in every practical sense, cut off from the civilization that built your spacecraft. The people who trained you, the engineers who designed your vehicle, the families who said goodbye at the launch pad, they all exist on a planet that you cannot reach, cannot speak to in real time, and cannot return to without enduring years of solitary transit through a void that stretches for billions of kilometers in every direction. The psychological dimension of this isolation is something that space agencies have only begun to study seriously. Experiments in simulated Mars missions, where small crews are sealed inside habitat modules for months at a time, have revealed consistent patterns of interpersonal friction, motivational decline, and cognitive fatigue. And those experiments were conducted on Earth, where the crew knew that the outside world was right beyond the walls, where emergency extraction was always possible, where communication with the outside was artificially delayed but never truly severed. A real interplanetary mission would strip away every one of those safety blankets. The crew would know with absolute certainty that no one is coming to help them, that no one can hear them in real time, that the nearest human being outside their spacecraft is months or years of travel away. The psychological architecture required to endure that reality without fracturing has never been tested under actual conditions. There is another consequence of interplanetary distance that rarely makes it into public discussions about space exploration, and it concerns consumables. Every kilogram of food, water, oxygen, fuel, spare parts, and medical supplies that a crew needs for the duration of a mission must be launched from Earth and carried aboard the spacecraft from the beginning. There are no resupply missions in interplanetary space. The International Space Station receives cargo deliveries multiple times per year. A crew on Mars receives nothing. Everything they will need for 2.5 to 3 years must be packed before departure. A single miscalculation, a single overlooked consumable, a single piece of equipment that fails without a spare could transform a survivable situation into a fatal one. And because of communication delay, Earth cannot improvise solutions in real time the way Mission Control famously did during the Apollo 13 crisis, when engineers on the ground worked in real time with the crew to jury-rig a carbon dioxide filter using materials aboard the spacecraft. That kind of minute-by-minute collaboration is impossible when the communication delay is measured in tens of minutes or hours. The consumables problem has a particularly cruel subset that deserves its own reckoning: medicine. A 6-person crew heading for Mars will include members with medical training. Some may be trained to the level of emergency physicians. They will carry a medical kit more comprehensive than anything aboard the International Space Station. But no crew of 6 can contain a fully trained surgeon, a dentist, an ophthalmologist, a psychiatrist, an anesthesiologist, and a radiologist. The human body is too complex and too fragile for a small team to cover every possible failure mode. And the farther you travel from Earth, the more medical scenarios cross the line from treatable to fatal simply because the right specialist and the right equipment do not exist within reach. On Earth, a ruptured appendix is a routine surgical emergency. An ambulance arrives in minutes. A surgeon operates within hours. Recovery takes weeks. The patient survives. On Mars, that same ruptured appendix requires emergency abdominal surgery in a habitat module with limited sterile space, limited anesthesia supplies, and a crew member whose surgical training may consist of a severe dental abscess that would be resolved in an afternoon on Earth becomes a source of escalating pain, infection risk, and potential sepsis when the nearest oral surgeon is 7 months of spaceflight away. A retinal detachment that an ophthalmologist could repair with a laser in a clinic becomes permanent blindness when no ophthalmologist exists within 400 million kilometers. A compound fracture requiring internal fixation, a kidney stone too large to pass naturally, an ectopic pregnancy, each of these is a manageable emergency on Earth and a potential death sentence in interplanetary space. Not because the conditions are inherently unsurvivable, but because the distance between the patient and adequate medical infrastructure is measured in months or years rather than minutes. The crew's medical kit, however comprehensive, is finite. It cannot be resupplied. The crew's medical expertise, however broad, has limits. It cannot be supplemented by a specialist walking through the door. And the communication delay ensures that even a consultation with a surgeon on Earth, transmitted line by line across a 22-minute gap, arrives too slowly to guide a real-time procedure. Every month of transit time added by greater planetary distance multiplies the number of medical emergencies that become unsurvivable. The human body does not pause its capacity for failure just because the nearest hospital is on another planet. And then there is the invisible assault that distance enables against the human body itself: radiation. On Earth, you live beneath a double shield. The planet's magnetic field deflects the majority of charged particles streaming from the Sun and from beyond the solar system. The atmosphere absorbs most of what remains. You spend your life bathed in a level of background radiation so low that your biology evolved to tolerate it without difficulty. The International Space Station orbits within Earth's magnetosphere, still partially protected. Crews on the station receive elevated radiation doses compared to people on the ground, but the exposure remains within manageable limits for missions lasting 6 months to a year. Step outside Earth's magnetic cocoon and everything changes. Interplanetary space is saturated with 2 forms of radiation that human shielding technology cannot adequately block. The first is solar energetic particles, bursts of high-energy protons and heavier ions ejected by the Sun during solar flares and coronal mass ejections. These events are sporadic but violent. A major solar particle event can deliver a dangerous radiation dose in hours. The second, and in many ways more insidious, threat is galactic cosmic radiation. These are extremely high-energy particles, mostly protons and atomic nuclei, that originate from sources outside the solar system: supernova remnants, neutron stars, and other violent cosmic phenomena. Galactic cosmic rays arrive continuously from every direction and carry so much energy per particle that they penetrate conventional spacecraft hulls as though the walls were not there. They pass through aluminum, through water, through human tissue, breaking DNA strands and damaging cells as they go. A 7 to 9 month transit to Mars would expose a crew to cumulative radiation doses that approach or exceed the career limits NASA has established for astronauts under current guidelines. A round trip, including the surface stay, would almost certainly exceed those limits. The biological consequences include elevated lifetime cancer risk, potential cardiovascular damage, and emerging evidence suggesting accelerated cognitive decline from sustained galactic cosmic ray exposure. For a multi-year transit to Jupiter or Saturn, the cumulative dose would be far higher, and no adequate shielding solution currently exists that does not add prohibitive mass to the spacecraft. The farther the destination, the longer the exposure. The longer the exposure, the greater the biological damage. Distance does not just isolate the crew from help, it irradiates them. Every additional month of transit through interplanetary space is another month of accumulated harm that no medicine aboard the spacecraft can reverse. The distance also determines the energy cost of travel in a way that compounds every other problem. Reaching Mars requires accelerating a spacecraft to a velocity of roughly 11.5 kilometers per second relative to Earth. Reaching Jupiter requires higher velocities or longer flight times. Reaching Neptune requires so much energy that no currently existing propulsion system can deliver a spacecraft to orbit around that planet in a reasonable time frame. Voyager 2 flew past Neptune. It did not stop. Stopping would have required decelerating the spacecraft by an amount roughly equal to the velocity it had accumulated over 12 years of flight. The fuel required for that deceleration would have made the spacecraft so heavy that it could never have been launched in the first place. Every outer planet mission to date has been a flyby for exactly this reason. The distances are so great and the energy requirements so extreme that even slowing down, let alone stopping and entering orbit, is often beyond our capability. Cassini achieved orbit around Saturn, but only by using an enormously complex trajectory involving multiple gravity assists and a large onboard fuel supply. No spacecraft has ever achieved orbit around Uranus or Neptune. This energy barrier has a cruel implication. The farther a planet is from Earth, the harder it is to stop there. And if you cannot stop, you cannot study the planet in sustained detail. You get a flyby. A few hours or days of close observation as the spacecraft screams past at tens of thousands of kilometers per hour. Then the planet recedes into the distance and you are left with whatever data you managed to collect during that brief encounter. Voyager 2's flyby of Neptune lasted roughly a day of close-range observation. All of our detailed knowledge of Neptune, its atmosphere, its rings, its moons, comes from that single day in August of 1989. One day of data for an entire planet, collected by a spacecraft that had been flying for 12 years to get there and could not stay because the distances and energies involved made staying impossible. This is what planetary distance does to human reach. It does not just make trips longer. It transforms the fundamental nature of exploration from something iterative, repeatable, and gradually deepening into something singular, precious, and vanishingly rare. On Earth, if a scientific expedition to a remote location produces interesting results, you send another expedition. You go back. You study the site in more detail. You build a research station. You return season after season until you understand it. In the outer solar system, you get one shot, one spacecraft, one flyby, one set of data that must sustain an entire field of research for decades, because nobody has the resources, the technology, or the time to go back. And this scarcity of access feeds back into the psychological relationship that humanity has with its own solar system. We speak casually about the planets as though they are places we know. We name their moons. We study their atmospheres. We plan future missions. But the truth is that our actual physical contact with most of these worlds has been fleeting, superficial, and separated by decades of silence. We have orbited exactly 4 worlds beyond Earth: the Moon, Mars, Jupiter, and Saturn. We have flown past Uranus and Neptune exactly once each. We have landed on the surface of only one outer solar system body, Saturn's moon Titan, and only once, over 20 years ago. The distances between the planets have not merely made exploration difficult, they have made it so rare that our entire species' direct experience of most of the solar system amounts to a handful of brief robotic encounters spread across half a century. The solar system that lives in your imagination, the one where 8 planets orbit the Sun in a reasonably connected system, where humanity might one day hop from world to world the way we hop between continents, does not exist. What exists is a scattering of isolated worlds separated by voids so wide that crossing them requires years of travel, where communication takes minutes to hours, where rescue is impossible, where launch windows are dictated by orbital mechanics on timetables measured in years, and where every mission is a solitary gamble launched into emptiness with no guarantee of return. The distance between planets does not just slow us down, it fundamentally limits what is possible. It converts the solar system from a connected neighborhood into a chain of outposts so separated from each other that each one might as well be its own tiny universe, adrift in a sea of nothing. And the most unsettling part is that we have not yet confronted the final truth about this emptiness. We have been talking about the distance between planets, as though the planets are the point, as though the worlds are the story and the gaps between them are just obstacles. But what if we have it backwards? What if the gaps are the story? What if the defining feature of the solar system is not the planets at all, but the immense, silent, crushing emptiness that separates them? That is where this story finally takes us. Strip everything away, remove the planets, remove the moons, remove the asteroids, the comets, the dust, and the ice. Remove every physical object orbiting the Sun and ask a simple question: how much did you actually take out? The answer is almost nothing. The solar system is approximately 99.86% Sun by mass. Everything else, every planet, every moon, every ring system, every boulder tumbling through the asteroid belt, every frozen nucleus drifting inward from the Kuiper belt, all of it together adds up to roughly 0.14% of the solar system's total mass. Jupiter alone accounts for more than half of that tiny remainder. The other 7 planets, combined, contribute less than Jupiter does on its own. Earth, the world we live on, the rock we have built civilizations across, the place where every human being who has ever existed was born and died, constitutes roughly 0.0003% of the mass of the solar system. If you rounded to 2 decimal places, Earth would not register at all. It would vanish from the ledger, a rounding error in the gravitational accounting of one ordinary star. But mass is only part of the story. Volume tells it even more ruthlessly. The Sun, massive as it is, occupies a tiny fraction of the solar system's total volume. The space claimed by the solar system, measured out to the orbit of Neptune at 30 astronomical units, is staggeringly vast. The Sun, despite being 1,000,000 times the volume of Earth, occupies just a few trillionths of the spherical volume enclosed by Neptune's orbit. A few trillionths. The planets fill even less. Jupiter, the largest of them, is 1,000th the volume of the Sun. Earth is less than 1,000th the volume of Jupiter. Add up every solid and gaseous body in the entire system, every planet, every moon, every asteroid, and their combined volume still vanishes into insignificance compared to the space those objects inhabit. You could remove every physical object from the solar system and the volume would not measurably change. The solar system, honestly measured, is not a collection of worlds. It is a collection of emptiness. The planets are interruptions. Brief, tiny, almost negligible exceptions in a volume dominated so thoroughly by vacuum that the matter within it barely registers. If the solar system were an ocean, the planets would not be islands. They would be individual grains of sand suspended in the water column, separated by kilometers of featureless depth. This is not poetry, this is geometry, and it is the single most important fact about the solar system that no diagram has ever conveyed. Consider what it would feel like to cross the solar system at honest scale. Imagine shrinking everything down so that the sun becomes a glowing sphere roughly the size of a large beach ball, about 60 centimeters in diameter. At this scale, Earth would be a small bead, barely half a centimeter across, sitting about 65 meters away from the beach ball. 65 meters of empty pavement between a beach ball and a bead you got ulus between your fingers. That is the Earth-Sun relationship at true scale. Mars would be a grain of rice, roughly 100 meters from the beach ball. Jupiter would be a plum, about 6 centimeters across, sitting about 340 meters away. Saturn would be a walnut, roughly 620 meters out. Uranus, a cherry, would sit over a kilometer away. And Neptune, another cherry, would be positioned nearly 2 kilometers from the beach ball. Now imagine walking this model. You start at the beach ball. You walk 25 meters and almost miss a speck of grit on the pavement. Mercury. You keep going. Another 20 meters and you pass a second bead, almost the same size as Earth. Venus. At 65 meters, you find a tiny bead. Earth. You stare at it. Then you look around. There is nothing else visible in any direction. You resume walking. 35 more meters of nothing, and you find a grain of rice on the concrete. Mars. You keep walking. 240 meters of absolutely empty ground with not a single object, not a single landmark, not a single interruption, and then a plum appears on the pavement. Jupiter. You have been walking for 340 meters, and you have encountered 5 tiny objects. Everything else has been blank ground. You keep going. Another 280 meters of emptiness to reach Saturn's walnut, then over 600 meters of nothing to find the cherry that represents Uranus, then another 700 meters of vacancy to reach Neptune. The total walk from your beach ball sun to the cherry at Neptune covers roughly 2 kilometers. And in that entire 2-kilometer walk, you have encountered exactly 8 objects, the largest no bigger than a plum, most of them smaller than a cherry. Everything else, every single step of those 2,000 meters, has been empty ground. Nothing to see, nothing to touch, nothing to find, just flat, featureless blankness stretching in every direction. That walk is the solar system. 2 kilometers of nothing interrupted by specks so small you could miss them if you blinked. And this model only covers the distance to Neptune. The actual solar system, measured to the outer edge of the Oort cloud, extends to roughly 100,000 astronomical units. At the beach ball scale, that would stretch your walk to over 6,000 kilometers, farther than the distance from New York to London. And in that entire intercontinental walk, the planets, all 8 of them, would be clustered within the first 2 kilometers. The remaining 6,000 kilometers would contain nothing but the occasional frozen pebble drifting through empty space. You would walk for months and never encounter a single object larger than a grain of dust. This is not a thought experiment designed to make you feel small. It is a description of reality. The solar system you occupy right now, at this moment, as you hear these words, is a structure defined almost entirely by absence. The planets exist, yes. They are real and they are magnificent, but they are marginal features in a landscape dominated so completely by vacuum that their presence is almost incidental. The solar system is not a system of planets. It is a system of emptiness that happens to contain planets, and that emptiness changes the meaning of everything we have discussed so far. The distances between planets are not gaps between destinations. They are the fundamental reality of the solar system itself. When you talk about the distance between Earth and Mars, you are not describing an obstacle that separates 2 significant objects. You are describing the condition that defines the solar system as a physical structure. The emptiness is not the space between the important things. The emptiness is the important thing. The planets are footnotes in a volume written almost entirely in vacuum. This inversion of perspective is what makes the true distance between planets so much worse than anyone imagines. It is not merely that the planets are far apart, It is that far apart is the default state of everything in the solar system, and the planets are rare, tiny, fleeting exceptions to that default. The vast majority of the solar system is not near anything. It is not in transit between anything. It is not a corridor connecting anything. It is just space, unimaginable quantities of space containing nothing, connecting nothing, leading nowhere. The implications for human expansion into the solar system follow directly from this reality, and they are far grimmer than the optimistic visions of science fiction suggest. When people talk about colonizing Mars, establishing outposts on the moons of Jupiter, mining asteroids, building habitats near Saturn, they are implicitly imagining a solar system where these destinations exist in some kind of accessible network. A solar system where reaching one world puts you closer to the next one, where infrastructure built at one location supports missions to another, where the human presence, once established in space, can spread outward incrementally, the way civilizations on Earth spread across continents, island by island, coast by coast. The actual solar system does not work that way. Establishing a colony on Mars does not make Jupiter more accessible. A base on Mars sits 1.5 astronomical units from the Sun. Jupiter sits at 5.2. The gap between them is 3.7 astronomical units, over 550 million kilometers. Building a city on Mars puts you no closer to Jupiter, in any practical mission design sense, than building it on Earth. The distances are so large and the energy requirements so extreme that each planet is effectively an independent destination, requiring its own launch, its own propulsion budget, its own multi-year transit from wherever your spacecraft happens to start. There is no stepping stone effect. There is no gradual expansion outward through a connected network of worlds. There are only isolated leaps across chasms that do not shrink just because you have successfully crossed a smaller chasm first. This is the fundamental difference between expansion on Earth and expansion in the solar system. On Earth, geography has friction but also connectivity. Oceans are barriers, but they also carry ships. Mountain ranges are obstacles, but passes allow transit. Every destination on Earth is connected to every other destination through a continuous surface that, however difficult to traverse, at least exists. The solar system has no such connectivity. Between every pair of planets there is nothing. No medium to carry you. No surface to traverse. No intermediate ports to shelter in. Just void. And the void does not care how advanced your technology is. It imposes the same brutal physics on every mission. Speed requires fuel, fuel requires mass. Mass requires more fuel to accelerate. The tyranny of the rocket equation ensures that every kilogram of payload sent to a distant planet costs exponentially more energy than the last. The distances between planets do not just challenge human engineering, they define the boundary conditions within which all human engineering must operate. This means that the solar system, as a place for human civilization to expand into, is not a frontier in the traditional sense. A frontier implies territory that can be gradually occupied, connected, and incorporated into a growing sphere of influence. The solar system is better understood as an archipelago of pinprick islands scattered across an ocean so vast that each island can only be reached by a separate, independent, enormously expensive voyage with no guarantee of return and no possibility of rescue. The islands are real. Some of them may be habitable, or at least survivable with sufficient technology. But the ocean between them is the defining feature of the geography, and that ocean is made of nothing. The psychological weight of this realization is something that humanity has not yet fully absorbed. We grew up with diagrams that showed the planets as neighbors. We watched documentaries that cut from Earth to Mars to Jupiter to Saturn in seamless montages, as though visiting each world was simply a matter of pointing a camera in a new direction. We internalized a mental model of the solar system as a tidy, comprehensible, connected place. And we have built our expectations for the future of space exploration on that mental model. We talk about Mars colonies and Jupiter missions and Saturn stations as though they are the next logical steps in a progression, the way building a railway across a continent is a logical extension of building a road between two cities. But the solar system is not a continent. It is not even an ocean. It is something for which human experience offers no adequate analogy. It is a volume of space so large that the objects within it are lost in it. The distances between those objects are so extreme that crossing any one of them is a generational undertaking, and the emptiness that fills the spaces between worlds is so absolute, so featureless, so devoid of anything resembling a landmark or a waypoint, or a reason to stop, that crossing it is not an adventure. It is an endurance test conducted in a sensory vacuum where the only scenery is the slow dimming of the sun behind you and the imperceptibly slow brightening of a pinprick destination ahead. There is a particular cruelty in the way the solar system is structured. The inner planets, the ones closest to us, the ones most accessible with current technology, are clustered within 2 astronomical units of each other. Mercury, Venus, Earth, Mars. They occupy a relatively narrow band around the Sun. This band contains the only planets humans have any realistic chance of reaching in the near future. And even within this band, the distances are severe enough that a round-trip mission to Mars takes years, and a rescue from interplanetary space is impossible. Beyond this narrow band, the distances explode. Each successive planet sits farther from the last by a margin that dwarfs the entire inner solar system. The gas and ice giants are not just far away, they are far away in a way that is categorically different from how the inner planets are far away. They are separated from us and from each other by voids measured in billions of kilometers, voids that require decades of flight to cross, voids where communication delays are measured in hours, and where the concept of human presence collapses into abstraction. The solar system, in other words, gives you a small neighborhood and then walls it off. It offers Mars as a plausible if terrifying destination, and then places Jupiter, Saturn, Uranus and Neptune at distances so extreme that reaching them with humans is beyond any currently foreseeable technology. It teases you with a cluster of rocky worlds and then reveals that the rest of the system, the giant planets, the icy moons, the rings, the storms, the subsurface oceans where life might lurk, all of it floats in a region of space so remote that even our fastest robotic emissaries need decades to visit and cannot stay when they arrive. And beyond Neptune, the cruelty deepens further. The Kuiper belt stretches from roughly 30 to 50 astronomical units. The scattered disk extends beyond that. The Oort cloud, that vast, spherical shell of icy debris marking the Sun's outermost gravitational influence, begins at perhaps 1,000 astronomical units and extends to 100,000. The solar system does not end at Neptune. It continues outward for distances so large that the planetary zone, everything from Mercury to Neptune, constitutes less than 1/3 of 1% of the total radial extent. The planets huddle in the innermost sliver of the solar system like a cluster of buildings at the entrance to a desert that stretches to the horizon and far beyond it. This is the true architecture of the place you live, not a compact system of neighbouring worlds, not a diagram that fits on a poster, not a series of colourful spheres arranged in a neat line. The solar system is a structure in which matter is so rare and so widely scattered that the overwhelming majority of the volume contains nothing at all. The planets, for all their beauty and complexity, are lonely specks adrift in an immensity that does not acknowledge their existence. The distance between any two of them is not a line on a chart. It is a gauntlet of vacuum, radiation, and silence that punishes every attempt to cross it with years of travel, hours of communication delay, and the absolute impossibility of rescue. And if this is what our own solar system looks like from the inside, if even the distance between planets within a single star system is this extreme, this hostile, this punishing, then the human future in space is not what the diagrams promised. It is not a gradual outward expansion through a connected neighbourhood of accessible worlds. It is a series of extraordinary, isolated, almost incomprehensibly difficult leaps between tiny islands of matter in an ocean of nothing. Each leap is harder than the last. Each destination is more remote, more cut off, more beyond the reach of help than the one before. and the spaces between those destinations grow wider and emptier with every step outward, until the very concept of nearness, of neighbourhood, of connection dissolves into a void that simply refuses to be crossed at any speed that human life can sustain. The distance between planets is worse than you think. Not because the numbers are bigger than you expected, although they are. Not because the travel times are longer than you imagined, although they are. It is worse because the distance reveals what the solar system actually is. It is not a family of worlds. It is a scattering of dust in a cathedral of emptiness. The planets sit so far apart that even the nearest ones test the limits of human technology and endurance, and the distant ones float in a realm so remote that reaching them is less like travelling to a destination and more like sending a message in a bottle into a sea without shores. Every diagram you have ever seen lied about this. Every classroom poster compressed the void between worlds until it looked like a comfortable gap. Every documentary animation flew between the planets in seconds, erasing years of transit with a smooth camera move. And in doing so, they left you with a picture of the solar system that is not merely incomplete, but emotionally reversed. They made you think the planets were the story and the space between them was blank filler. The truth is the opposite. The emptiness is the story. The emptiness is the defining feature. The emptiness is the thing that makes the solar system what it is. A vast, cold, indifferent arena where tiny worlds orbit in total isolation, separated by distances that mock the very idea of neighbourhood. The next time you see a diagram of the solar system, look at the spaces between the planets, the blank white gaps that the artist left between the colourful dots. Those gaps are where the truth lives. Those gaps are where the years of travel hide. Those gaps are where communication dies, where rescue becomes impossible, where the human reach falters and the void wins. The planets are the decoration, the emptiness is the architecture, and the architecture is so much larger, so much harsher, and so much more indifferent than any picture has ever shown you. If even the distance between planets in our own solar system is this savage, then the future of humanity in space was never going to be easy. It was never going to be a steady expansion outward through a friendly cosmos. It was always going to be a confrontation with emptiness on a scale that human intuition was never designed to face. The diagrams hid that truth. The numbers reveal it, and once you see it, you cannot unsee it. The planets are real. They are beautiful. They are out there right now, orbiting the sun in their ancient paths, but between every one of them lies a silence so vast and so absolute that the word distance does not do it justice. What lies between the planets is not a gap. It is the solar system itself in its truest and most honest form, and it is far, far emptier than you ever imagined.